Good evening, dear colleagues, and welcome to our concluding lecture on quantitative research methods in psychology. Obviously, our course would not be complete if we did not discuss factor analysis, the favorite method of psychologists, created by psychologists and for psychologists. So today we'll take a little quick look at exploratory factor analysis, which I hope maybe you have already encountered before in your homeworks and in your seminars. So today I'll just discuss some of the more theoretical aspects that you might need to be aware of. And then I will make a brief introduction to confirmatory factor analysis, which in fact is not as scary as it seems. Essentially, it's not so difficult to do it as long as you know where to do it and how to do it. So today we'll discuss this, and to complete it, we'll take a quick look at another couple of methods that are fairly useful for us as psychologists and that have been used quite successfully for the development of various psychological theories: cluster analysis and multidimensional scaling. So without further ado, let's explore exploratory factor analysis. So here on this slide you can see a little diagram where you see that there are some rectangles showing different variables, and now we know that rectangles denote observed variables as we saw them in path models. But unlike path models, here you can see that there are also some strange ellipses or circles, and those ellipses and circles denote latent variables, variables that are not measured but are estimated based on a bunch of observed variables. For example, we have 6 questions in our questionnaire. Maybe some of them tap into anxiety, some maybe tap into depression, and some tap into aggression or whatever. And for each of these questions, for each of these observed variables, we want to find out which of these latent unmeasured dimension does it relate to. And this is essentially the task of exploratory factor analysis. As I just said, exploratory factor analysis was invented originally by psychologists. In the 1930s, it was Charles Spearman who was interested in the structure of human intelligence. And he was wondering, his main question was whether there is a single general factor of intelligence, general ability, or all those different abilities are specific and there is no single dimension behind them. So essentially for this task he created exploratory factor analysis, which existed for a while, and it was probably #1 method for psychological studies in the 1960s and 70s. But then in the late 1970s, another researcher, a mathematician and also a social scientist, Karl Jureskog from Sweden, combined the path analysis framework, which we were discussing yesterday, and latent variable approaches. So essentially he joined together path analysis and factor analysis into a single framework, which we now call structural equation modeling. So essentially structural equation modeling is a whole bunch of linear models that can be modeled there, from simple correlations to models with observed variables, and finishing with more complicated models with latent variables. So what do we use exploratory factor analysis for? Essentially, the task is to reduce the number of dimensions. We have a large correlation matrix with maybe 50 or 100 questions in our questionnaire, and we want to see if these individual questions can be reduced to more general dimensions based on their shared variance. So we expect that all questions that measure the same thing should form a single dimension, because this latent construct, unmeasured construct, reflects in their shared variance. Essentially, all questions about depression, people who are more depressed will be more likely to say yes, and who are not depressed will be more likely to say no, and so on. And these latent dimensions that we try to uncover, we call them factors. But as we discussed in ANOVA, the word factor comes from Latin facere, which kind of assumes that there is some kind of causality. that this hidden dimension might be a common cause of all these observed indicators. But in fact, in a modern factor analytic approach, we all recognize that this is not the case. There is no causality that can be inferred or assumed. Essentially, we just look for bunches of variables that have some shared variance. And what is the cause of this shared variance? It can be completely different. In psychology, we often use exploratory factor analysis when we want to find out the structure of a new questionnaire. You came up with a bunch of items and you want to explore what kind of dimensions do they measure. Do the items work the way I expected them to work? Sometimes we also use exploratory factor analysis to explore how scales from different questionnaires, do they have single dimensions behind them? For example, we can factor analyze a whole bunch of intelligence tests to see which of those tests are more likely to measure verbal ability and which of them are more likely to measure mathematical ability, and so on. And of course, nowadays, because of its limitations, exploratory factor analysis is mainly used as a first step before the application of more advanced statistical models that we'll also discuss today. Before we begin the discussion of exploratory factor analysis, it makes sense to remember a very important warning made by Barbara Tabachnik, the authoress of a wonderful textbook on multivariate methods, where she writes literally that factor analysis is frequently used in an attempt to save poorly conceived research. If no other statistical procedure is available for your data, at least you can always factor analyze your data, get some results. And people have been abusing this practice so much that in the minds of many, especially reviewers, exploratory factor analysis is associated with sloppy, dodgy research. The very power of principal component analysis and factor analysis to create apparent order from real chaos contributes to their somewhat tarnished reputation as scientific tools. So that's the reason why if you want to publish a paper, probably exploratory factor analysis will not be sufficient. But we'll soon see why. So what are the assumptions of exploratory factor analysis? Basically, it takes a correlation matrix, and it's a Pearson correlation matrix normally in most statistical packages. That's why the same assumptions: interval, scale, multivariate normality, linear associations. Of course, people have been applying exploratory factor analysis to data that are not perfectly normal, not perfectly interval scale, and research has found that if your ordinal scale has approximately normal distribution, and if you have at least 4 or 5 better categories in that scale, then you can just apply good old standard exploratory factor analysis and not really worry much about. The real problem that you can encounter: never apply exploratory factor analysis to matrices of dichotomous binary variables. If you have a test where the answers to individual questions are yes and no, or it's an ability test where you just quantify if a person has solved a task or not with 1 or 0, if you apply exploratory factor analysis to such a data matrix, as a result, you can see a factor structure where in fact there is none. And for this kind of data, what you need is a tetrachoric correlation matrix, or for ordinal data, you can use polychoric correlation matrices. Unfortunately, these are not available in SPSS, but in other SEM structural equation modeling software, you can easily find these capabilities. And also other software packages like Amos and Plus they can make adjustments for non-normal distributions. They can make adjustments for clustered samples to avoid having aggregation bias in your factor structure. You can even do a two-level exploratory factor analysis to see what kind of factors are there at the level of individuals and at the level of groups. M+ allows you to do it quite easily. And you can even model other theoretical distributions, like skewed distributions instead of normal. But of course, you probably will not need those advanced things. Just in case if you need them, you can always be aware that they exist. Another very painful issue that is associated with exploratory factor analysis is the issue of sample size. How many participants do I need in my study for my questionnaire in order to be able to factor analyze it? And some textbooks provide some kind of rules of thumb. For example, that the ratio of observations to variables should be at least 5. Or some authors say at least 10. And still other authors say at least 100 people in your sample. Well, in practice, all these rules of thumb are completely imperfect. Because in fact, your optimal sample size depends on how much error there is in your data. If your individual variables are self-report items, they are not reliable, and you need a larger sample in order to be able to uncover latent dimensions. And even then, the variance explained by a good model will not be very high. If you see 30 or 40% of explained variance, this is totally all right if you're factor analyzing items. And in this case, I would totally recommend you to have at least 10 participants per question if you have maybe 20 questions or so. But of course, if you have 60 or 80 questions, it might be very hard to get a sample of 600 or 800. So, well, then there's no problem. Try to get maybe at least 300-400, and that should be fine. And if you're factor analyzing scales of existing questionnaires that are very reliable, you can get away with even a smaller sample. With a sample of even less than 100, you can get a meaningful structure. But essentially, the larger is your sample size, the more confident you can be in your factor loadings. In a smaller sample, you can only rely on large factor loadings. In a large sample, even small factor loadings can be substantive and not random. But we'll discuss that quite soon. So when we conduct an exploratory factor analysis, the input data are our raw data or a correlation matrix that we feed to the software, and the output is a matrix of factor loadings, which show the relationship between each variable and each of these latent dimensions that we have discovered. Also, we see how much variance is explained by each dimension and by the model as a whole. And we see how much variance of each individual variable is explained by this factor model. Optionally, we can also request SPSS to give us factor scores, basically individual scores of people on those latent dimensions. And we can also request residual correlations to see which of the associations in our data are not explained by our factor model. So let's just go through factor analysis step by step to see what kind of choices we make and how we make them at different stages of exploratory factor analysis. The first choice that we inevitably make is the choice of variables. How do we choose variables for factor analysis? Well, first of all, if you want to factor analyze something, you need to plan ahead. What kind of latent dimensions do you expect, and how many variables do you have for each of these latent dimensions? The minimum requirement for exploratory factor analysis is to have 3 variables or 3 indicators, as we say, per factor. So at least 3 questions if you want to measure some construct. But of course, if you have a little bit more, you can be more confident, because sometimes it happens that a single question maybe does not work, and you are left with only 2 questions, and then a factor might not quite well emerge, depending on how homogeneous these questions are. So it's better to have more indicators, and you will get better structure if the number of questions for different scales is comparable, and the homogeneity, how much similar or different these questions are, is also comparable. And sometimes you might have problems if the relationships in your dataset between variables are a little bit tricky. For example, there is some kind of hierarchical structure between of the associations between your variables. For example, items form scales, and scales form some larger second-order factors, but several of them. As a result, exploratory factor analysis may have a problem. Some of these factors will be reflecting lower level associations, some higher level, some kind of mixture. And also sometimes we have questions that differ more than on one basis. For example, you have questions in your questionnaire about anxiety and depression, and you also have forward scored and reverse scored questions. So if you factor analyze such data, you're going to be lucky in case if you see separately forward scored anxiety, forward scored depression, reverse scored anxiety, reverse scored depression. It is very likely that your factor structure will reflect a mixture of the two, because exploratory factor analysis just does not do a very good job of dealing with such complex data sets. And there are some potentially useful statistics that SPSS can give us, KMO and Bartlett's test of sphericity, that we'll talk about a little bit later. The most important rule associated with exploratory factor analysis is called garbage in, garbage out. Your analysis is only as good as your data, but there are two reasons why you may have garbage out as a result of your analysis. You may have garbage data that is completely does not fit with assumptions or just contains some kind of errors. And then even if your choices are perfect, if your model is perfect, you'll get garbage results. But if you have perfect data, but you choose a garbage model, then you can also have garbage results. So we'll discuss how to avoid both of these possibilities. And that was the first choice. How do we choose what to factor analyze? So try not to factor analyze any kind of garbage, just because the result can be quite sloppy. But if you have chosen some good variables that you expect to have some latent dimensions behind, the second choice that you face is the choice between two principal methods. One is called principal component analysis, and the second bunch of methods are called jointly factor analysis. What is the difference between those two? Sometimes in the textbooks, when people say factor analysis, they mean both principal components and common factor analysis. But there are some differences that can be very important occasionally. Principal component analysis is a much simpler method that tries to take your correlation matrix, tries to find its eigenvectors and eigenvalues, and essentially in the process it tries to describe all the variance in your data. As a result, this simple approach is more optimal for situations when you have no assumptions about your factors. You don't have any expectations. You just want to describe this bunch of variables and then see if the dimensions make sense. Another family of methods called factor analysis proper or common factor analysis are the methods that are based on principal component analysis initially. But then there is an additional optimization stage. And as a result, common factor analysis aims only to describe the shared variance of a bunch of variables. Only the common variance of your variables is taken into the factor model. As a result, you will see that there is one important difference. If you have a single variable that has nothing to do with any other variables, it does not have much shared variance with any of them. In principal component analysis, you will see such a variable as a separate component, a separate dimension. In factor analysis, this variable will not contribute to any of the factors. Hence, it's no surprise that in natural sciences, where people try to describe some kind of real data sets, they use principal component analysis. In social sciences and psychology, we typically use factor analysis proper methods like maximum likelihood or weighted least squares or minimum residual, because we normally have expectations about common factors in our data sets. In practice, of course, the structure that you see from both methods is usually very similar, so the differences are quite minuscule, but some reviewers really care about them. So you have chosen whether to use principal component analysis or factor analysis. What happens next? Essentially, when the algorithm analyzes your data, it starts with the extraction of principal components. Principal components are basically dimensions in the space of your variables, dimensions that try to explain the most variance. So here you can see a very simple example where there are just two variables, let's call them x and y. And obviously the maximum number of dimensions can also be no more than 2. because for a two-dimensional space, you don't need more than 2 dimensions to represent it. But just as an illustration, so the first axis of the first principal component tries to find a regression line which would capture most of the variance between the items. And then the next one is drawn orthogonal to the first one. So it's perpendicular. And also, if you have more dimensions than 2, it tries to place it in such a way that it would capture the most of remaining variance. And in this way, factor analysis goes on extracting those principal components until the number of these dimensions is equal to the number of your variables. And then we can say that these dimensions, they have explained 100% of our variance. But of course, what we want is a minimum number of dimensions that would explain the maximum amount of variance. How do we make that decision? And this is where the third step comes, choosing how many factors do you need for your exploratory factor model. And there are different criteria that you can use. The most straightforward and somewhat stupid criterion is called Kaiser criterion, and it is the least optimal, but it is the default in SPSS. And it's very easy to find out a person who, if you read a paper and you see the person is saying, oh, we conducted factor analysis in SPSS and SPSS gave us 5 factors. Well, if SPSS gave them 5 factors, it means that the person does not understand the whole logic of factor analysis because they were relying on this Kaiser's test by default. And Kaiser's test tries to pick the number of dimensions with eigenvalues above 1. Basically, an eigenvalue of 1 corresponds to the contribution to variance comparable to that of one variable on average. So the logic of Kaiser when he proposed this was if a factor weights more than one variable, probably it makes sense. But if less, maybe it makes no sense. But unfortunately, the results of this criterion will be different depending on how much noise you have in your data. So sometimes it will give you too many factors, sometimes too few. That's why it's best not to use it. A much better criterion, Kettle's test, scree plot, which I will show you what it looks like very soon. Also, some people say, let's try to rely on explained variance. Let's try to create a factorial model that would explain a certain proportion of variance of our variables. Maybe in natural sciences this works. In social sciences this does not work at all, because how much variance you need to explain, that depends on how much error variance you have, which you can never explain. And you don't know how much error variance you have, because you don't know how reliable your variables are. That's why this criterion is definitely bad. Don't ever use it. And if you are really rigorous, you can use parallel analysis or minimum average partial. These are available in R. There is a nice package psych, or in SPSS there are macros which can compute those for you. So if you really want to justify well the choice of number of factors, you can use these more rigorous statistical tests. But usually we are quite comfortable with just a simple Kettle's scree plot. What is a scree plot? Essentially, it's a type of diagram where on the horizontal axis we plot the number of components that we are extracting, the number of dimensions that we are extracting, and on the vertical axis we plot eigenvalue, the weight of this dimension, which is proportional to the variance explained by this dimension. And Kettle's idea, why it's called a scree plot. Well, imagine that it's a hill or a mountain, and at the bottom there is a ravine where there is some kind of rubbish, some small stones like scree. So your goal is to ignore this bottom of this ravine and only take the points that create the slope above the point where this line kind of cracks. So based on this diagram on the right, I would definitely choose 2 factors. Unfortunately, sometimes it's a little bit more tricky. If you take a look at this diagram on the left, you can see that maybe you need 2 factors, or maybe even 4, because there are several points where this line breaks. So sometimes it's hard to decide. But usually, if you have a clear factor structure, you see this picture on the right. Ironically, these two script plots come from the same questionnaire used in two different samples, and just one item changed. So we can only wonder what has affected this sample on the left. Okay, so your goal is to choose a minimum number of dimensions that explain the maximum proportion of variance. And basically, you take these points on top of this line. After you make a decision of how many dimensions you need, you make the next and the final decision. How do we rotate these dimensions? Because by default, these dimensions will be directed in the direction of explaining the first one explains maximum variance, the second one explains the remaining variance, and so on. From the point of social sciences, this is not what we want. Because if you have, for example, questions on anxiety and questions on depression, the largest variance will be related to general psychological problems. And the second dimension might be related to the differences between anxiety and depression. So it will not be very interpretable. That's why what we want, after we have picked the number of dimensions, we try to orient them in this space defined by our variables in such a way as to make sure that our model becomes more interpretable. And here we make the choice between two types of rotation. The first type is called orthogonal rotation, which gives you uncorrelated factors. So factors are perpendicular, like this. Their correlation is exactly 0. With oblique rotation, factors can correlate. So they can go in kind of the same direction. For example, if you're measuring anxiety and depression with your questionnaire, we know quite well that these psychological problems often come together. So it would be more logical to use oblique rotation. Actually, most methodologists say that for psychological applications, having oblique rotation is better by default. And unfortunately, traditionally, people have often been using principal component analysis with Varimax, which is orthogonal rotation. And for many situations, this was not optimal. So this practice, which was called little jiffy for some reason, it's often criticized. So now reviewers are definitely very skilled in those things. Just to show you a little illustration of how rotation works. Varimax is an orthogonal rotation. Why is it called Varimax? Because it tries to maximize the variance of loadings of our variables for each factor. So that as a result, for each dimension, the variables should have either very high or very low loadings. And as a result, we can arrive at what is our ideal, the ideal of a simple structure where each variable is only related to one factor and is related to the minimum extent to the other factors. So it is based on this assumption that we should get this simple structure that Varimax performs its rotation. And essentially, with two factors, it is basically a rotation. Imagine that you're rotating a sheet on which these variables are plotted. And from the picture on the left, we just take a certain angle and we come to picture on the right. So nothing else happens. But here you can see that on the left, we had some variables with kind of average loadings on both factors, and this model was hard to interpret. But with the picture on the right, we see that some variables have high loadings on factor 1 and low loadings on factor 2, and some variables have high loadings on factor 2 and low on factor 1. As a result, it is very easy to interpret this model and to put those variables into two groups, basically two subscales. So so this was a little theoretical introduction into exploratory factor analysis. Just a couple of words about its limitations. The main problem of exploratory factor analysis is that the variance that is not explained is not separated into random error and bias. So essentially, if we did not explain some variance with our model, we can never be sure if this random error, which we can ignore, or this is some shared variance between variables, and maybe there are some additional dimensions that we cannot ignore if we want to describe our data. Unfortunately, exploratory factor analysis does not allow us to see this picture clearly and make this decision. And another problem is that this model is essentially too flexible. All variables are related to all factors. But do we need questions about anxiety to have relationships with depression? Maybe not. As a result, this model is very unstable. It needs fairly large samples to converge. And also some of these loadings that are there by chance are still substantial in magnitude. As a result, we cannot even compute good factor scores because they are influenced by all variables, not only those that are related to this particular factor. So it has quite a few limitations, but still it's the first step in our analysis. Now let's take a look at an empirical example of exploratory factor analysis. As an empirical example, I have taken data that come from a British website where 450 individuals have completed a scale which is called Positive and Negative Affect Schedule, PANAS. And basically it's 20 emotional terms that are rated on a 5-point Likert scale. To what extent did you feel those during the last 2 weeks, I think we used. And what we want to find out, what dimensions are there in this set of 20 variables. And in SPSS, we go to Analyze Dimension Reduction Factor Analysis, and there we make all these choices about our analysis. First, of course, we go to the extraction dialog, where we need to choose a method of factor analysis. Here I chose maximum likelihood. Don't forget to order a script plot. And here I set a number of factors that I expect 2 factors based on my theoretical expectations. Then, if you don't know how many factors do you need, well, you can order a larger number of factors and see what happens, or you can order a smaller number of factors and see what happens. But you'll definitely want to explore the script plot first before deciding how many factors you want. And sometimes it's very hard to decide because different factor structures can describe the same data set. Basically, you can think of the number of factors as a magnifying glass. The more factors you have, the more details you have about the associations of your variables. But do you really need all those details? Well, that's up to you. So definitely you need to stop at some point with a minimum number of factors that gives you a good representation of your data. And finally, we go to this rotation dialog, and we choose a rotation type. So here I chose direct doubly-min because I want to have correlated factors by default. If I did not, I would choose Varimax. Another oblique rotation here is Promax, but Promax is obsolete. Oblimin is much better. Yeah. So what does SPSS gives us in terms of results? First of all, we get this KMO and Bartlett's test of sphericity, which kind of try to give us some information about our data. KMO tries to quantify the proportion of shared variance by variables, and the larger is the better. So here it's 0.90, it means it's very good. And Bartlett's test tries to test if our matrix is different from a matrix of uncorrelated variables. And also, if it's significant, it's good. But essentially, they are not very informative. I normally just don't look at them at all. Just some people ask questions about them. Yeah, and here is the script plot. So if we took Kaiser's default criterion, it would give us 3 factors, because for the third factor, the eigenvalue is something like 1.18. But of course, by looking at the script plot, we see that probably 2 dimensions are enough to represent this structure sufficiently well. And that's why we order 2 dimensions. And finally, if the number of dimensions that we chose is what we want, we can take a look at communalities and at variance explained. This variance explained table tells you the proportion of variance of your variables that is explained by the model as a whole. The left part reflects initial components. So 1 dimension would reflect 34%, then 2 dimensions 49%, 3 dimensions 54% together, and so on. But these are original dimensions, and you see that each additional dimension explains a smaller and smaller proportion of variance. But if we rotate them, after rotation, the picture changes a little bit, and the proportion of variance might be completely different. And communalities are essentially the proportion of variance of each variable that is explained by the factor model. And here we see that generally they are fairly good, but there are some variables that contributed less to this factor model, like for example irritable with just 0.17, so only 17% of its variance is explained by the factors, and so on. So maybe it's just not a very good indicator. Factor loading plot, which shows us there are 2 neat bunches, positive emotions and negative emotions, very nicely spread across 2 dimensions. There is nothing in the middle. But when you look at this picture, don't be too optimistic, because if you have an oblique rotation, SPSS plots you these oblique correlated factors on an orthogonal bunch of axes. I don't know why. And the most important, finally, the most essential part of our analysis is the matrix of factor loadings. What are factor loadings? Essentially, you can think of them as being the same as correlations and beta regression coefficients. Basically, they reflect the relationship between a variable and a factor. 0 means no association, and 1 means perfect positive association, and -1 means perfect negative association. So in order to interpret the meaning of each factor, we need to see which of the variables have the highest loadings on this factor. And these loadings are supposed to be substantial. Like if it's 0.7, it means that about 50% of the variance of this variable is related to this factor. But if this loading is only 0.3, it means that only 10% of variance of this variable is related to this factor. And of course, this variable maybe is not very important to understand the meaning of this factor. So normally I begin with variables that have the highest loadings. And here, for example, for the first dimension, we have the highest loadings for enthusiastic and excited, interested, alert, inspired, and so on. So essentially, they are all positive emotions here. And on the second factor, we have negative emotions. So it's quite easy to interpret that the first dimension is positive affect and the second is negative affect. And here there are no variables that would have comparable loadings for both factors, which is a very good idea, which is a very good sign that these dimensions are clearly separated. Because if we have variables with almost equal loadings on both factors, probably they tap into some more general aspect of what we are trying to measure. And maybe if we want to have discriminant validity for our factors, we usually remove such variables to ensure that our factors are clearly separated. Yeah, how large are the loadings that you need to take into account? Well, it depends on your sample size. But of course, in larger samples, even loadings like 0.2 can be meaningful. But if the loading is 0.2, it means that 2.2 squared is only 4% of variance that this variable contributes to this factor. And probably it's not important anyway. So I would say above 0.3 or 0.4. Yeah, and this was, of course, a 2-dimensional model. What would happen if we take a 3-dimensional, a 3-factor model? The third factor would explain some very small proportion of variance, only 5%. But if we look at it at this three-dimensional model, we see that the first two factors are pretty much the same, a positive affect and negative affect, but the third dimension, it only includes two variables, guilty and ashamed. So why do guilty and ashamed form a single dimension? Well, basically we need to think, is there any reason why people who feel guilty also feel ashamed, and those who don't feel both of these emotions? And of course, we can think that maybe this is self-conscious negative affect or some kind of social negative affect. And with three dimensions, it basically separated from negative affect in general. So here, the loadings of these two variables are now close to 0. And this is basically your choice. Do you want to have two dimensions or do you want to have three? It's totally up to you. But if you have a factor with just two variables, probably if you want to have a separate scale, it will not be very reliable, and also the measurement precision will not be very high because there is a small number of questions. So probably it makes little sense to separate a separate factor with just two questions. And of course, the order of these factors is not so important, and even the sign of these factors. Some of these loadings are positive, some of these loadings are negative, but essentially this sign is completely arbitrary, and you can always flip it. So if your factor is in the opposite direction of what you want, you can just inverse all the signs of all the loadings, change plus to minus and minus to plus, because the model is mathematically equivalent. It's just a different rotation, and that's it. And of course, in Jamovi, you can also conduct exploratory factor analysis very easily. Just select the variables that you want to factor analyze. And here, you can not only rely on scriplot, but you can also rely on parallel analysis, which shows you eigenvalues for factors discovered in random datasets and eigenvalues for factors discovered in your dataset. And your goal is to pick those that differ from random eigenvalues. And here you see that for the first two dimensions there is clear separation, but for the third dimension it's already not so clear. It's just only slightly above the random eigenvalue. And probably this difference is not significant. R uses a more rigorous approach with 95% percentile, and there it would definitely not take this third dimension. Basically, the results should be almost exactly the same if we choose the same types of rotation. The only difference is that this matrix looks now much nicer in Jamovi because it sorts questions in order of descending factor loadings. So if you want to publish it, you just take it and publish. What happened with irritable? Probably the loading was low, and yeah, so maybe it's best to disable hide loadings, because normally we are supposed to present all the loadings in our matrix. So just a brief conclusion. Exploratory factor analysis is our used to be #1 method of psychologists. It's a good way to explore the structure of a set of variables. But of course, there are some challenges, some disadvantages. First of all, the rotation algorithm, it's completely arbitrary based on mathematical criterion. It does not know what kind of structure you expect to find. So it does not always reveal an optimal solution. In many cases it does, but not always, because sometimes if your structure is more complicated, then try exploring different rotations. And the main limitation is that all the loadings are included by default, even those loadings that are not supposed to be there, irrelevant ones. For example, our positive emotions, they have nothing to do with negative affect. So we don't need those loadings, but they are there in the model. As a result, the model is not very stable, it's very sample dependent, and it's impossible to know if the model explains the data well. And of course, that's the reason why exploratory factor analysis is hard to publish nowadays. And because so many sloppy researchers have abused this method, when they said, okay, I have a bunch of variables, I don't know what to do with them, I'll just factor analyze them and describe the dimensions. But guys, factor analysis does not create any meaning, does not create any sense in this data set. This meaning can only be created by a theory, and if you have no theory, don't factor analyze anything. Please do not contribute to the tarnished reputation of this very nice and very useful method. So now let's take a look at its contemporary counterpart, confirmatory factor analysis.